Hi Math 135, what's up? In this video we're going to look at some examples from section 6.1. These examples are hopefully going to help you understand the concepts from 6.1 a little bit better, as well as work through some problems that are comparable to your homework problems. Not all of these problems are comparable to homework problems, but some of them are. Looking at this first one, we're trying to understand the distinction between the notions of subset. Remember this symbol means subset. So understand the subset relation between sets. So remember, A is a subset of B. If all elements of A are also elements of B. So the idea is we took some of, if we want to build a subset of B, we just root around in B, see what's there, and take a few things. Maybe take all the things or none of the things. But most subsets, we take some of the things, but not all of the things. Okay? So in part A here, we have the set that just consists of the single element 1 and its relationship to the set. Remember, these brackets indicate set, the set that consists of the elements 1 and 2. And if I look, I guess if we're thinking about this as being set A, and this as being set B, in order to build set A, I looked around in B and found some things that I wanted. In this case, I just took the 1. So yes, this is a subset. Now, just remembering the element relation, 1 is an element of A. And it's also, 1 is also an element of B. 2 is also an element of B. It's one of the things in the set B. All right, looking at our second example, example B here, we have the set consisting of the elements 3, 4, and 5, as well as the second set that just consists of the elements 3 and 5. In this case, the first set is not a subset. Not a subset of the second one. It's got an element. There's an element here that doesn't show up over here. All right, so I introduced something new. Now it is the case that the set 3, 5, or the set consisting of the elements 3, 5, is a subset of the set consisting of the elements 3, 4, and 5. Because everything I see over here also shows up over there. In C, we're comparing the set consisting of the elements 7 and 9 with the set consisting of the elements 9 and 7. These two sets are equal. They have the same elements. Remember the order, when we're talking about sets, we're not so concerned about the order in which they show up or the way in which the set is described. We only care about the elements that are there. And every element that shows up in this set also shows up in this set, and vice versa. Okay? So we could also say that the set consisting of the elements 7 and 9 is a subset of the other, because, again, everything that shows up on the left also shows up in the set on the right. And similarly, we could say that the set consisting of the elements 9 and 7 is a subset of the set consisting of the elements 7 and 9. Again, we're not so much concerned about the order. The point here is that everything that shows up in the left set is also an element of the right set. D is a similar situation to B, where we have an extra item here that doesn't show up on the right. And so this is not a subset. So the line below the subset symbol doesn't make a whole lot of difference. Now, in other math classes, we might use the backwards subset symbol. Like, that's a legitimate thing to do, but that's not ever something that they're going to ask us to do in Math 135. Looking at example E, the bracket notation here indicates the empty set. It's the set with nothing in it, with no elements. The set with no elements, remember, that's the empty set. This 0 with a cross through it is another notation for the empty set. So these are two different notations for the empty set, right? So it's just the same set by default. It's just two different names for the same set. The example in F is a little bit tricky. The set on the right is the empty set. The set on the left is the empty set. The set on the right is the set with a single element, which is also the empty set. Okay, one of the set theory starts to get a little bit confusing till you get over it. When you realize that sets themselves can be objects and elements of other sets. All right, and so one of the things that we can notice here is that the number of things, if I call this set A and this set B, the number of things in set A, this is 6.2. This is 6.2, so if you want to brush up on your notation involving cardinalities, the number of things that are in A is the empty set. It has no elements. So the number of things in the set A is 0, whereas the number of things in set B is 1. There is a single element in set B, the empty set. All right? Now, so these two sets are not equal. These two sets are not equal. If they were equal, and you can kind of think about this, if two sets are equal, they should have the same number of elements. And these two sets do not have the same number of elements. What is true, and this is also a little bit confusing, is that the empty set is a subset. Right? The empty set is always a subset. No matter what set A is, the empty set is always a subset of A. All right? And that's just because all of the elements in the empty set are also elements of this set. It just so happens that we can say that that's true because there are no elements that we're talking about. It's a weird thing. It's better not to worry too much about why that's true. Just understand that the empty set is always a subset. Okay? That's what we want to focus on. Okay? All right, moving on to example 2. We have a universal set is given. The universal set is the set of X such that, is how we read this bar, the set of X such that X is a positive integer no more than 13. So we're using the set builder notation to describe our universal set. We also have set builder notation for the set A. A is the set of X such that X is not a multiple of 3. And I guess when we're presented with this universal set, we're assuming that, all right, we're talking about all of the X's in the universal set, all of the elements in the universal set that are not multiples of 3. Right? B and C are both given using roster notation. And we can see that, well, once we write down our universal set in roster notation, we'll be able to see that B and C are also subsets of our universal set. All right. So we want to write our universal set using roster notation. They've described our universal set. We just have to list the elements. We want a positive integer no more than 13. All right, so the positive part means, well, let's talk about the integer part. Integer means whole number. Okay, so we want whole numbers. We want positive whole numbers. And no more than 13 means less than or equal to 13. Right? 13 is itself no more than 13, and everything smaller than 13. So we got like 3 different things that we got to satisfy here. We want our whole number to be a positive whole number, and for that positive whole number to not be any bigger than 13. So we have basically the whole numbers 1 through 13. And this is one of those sets where it gets a little bit obnoxious writing it down in roster notation, but there's only 13 elements. In the grand scheme of things, 13 is a pretty small number. But we can kind of see the benefits of using the set builder notation just to describe this set. It's easier to describe it than it is to write it out in roster notation. All right, when we write down the set A using roster notation, remember A is not, we want all of the numbers that show up in our universal set that are not multiples of 3. So we're basically throwing away 3, 6, 9, and 12. All right, 1 and 2 are not multiples of 3. 4 and 5, 7 and 8, 10 and 11, and 13. So those are the elements of our universal set that are not multiples of 3. The complement of A, that's what the superscript C means. The complement means all the things that are not the set of X, such that X is not an element of A. So that would be a set builder way to describe the complement. We just want to pick the things that are not in A. All the things in our universal set that are not in A. Well, if A was the things that weren't multiples of 3, we could also kind of negate that, a set of X such that X is a multiple of 3. Kind of like a double negative here. Not. X is not a multiple of 3. Or X is a multiple of 3. So we're just writing down the multiples of 3, or all of the things that we left out of A. 3, 6, 9, and 12. Okay. For this next one, A intersect A complement, or the intersection, that's what this symbol stands for, the intersection of A and A complement. We want all of the things that are in both sets. Now, you can kind of think of A and A complement as opposites. In a certain sense, they are. A and A complement are never going to share elements. Right? When we're looking for the intersection, we're looking for all of the elements that are in both sets. And when we're talking about a set and its complement, you don't have any elements that are in both sets. Okay? If we just focus on the smaller of the two sets, look at A complement, say, all right, 3 is our first candidate to be in both sets, but it doesn't show up here. It doesn't show up in our A set. Same thing for 6, 9, and 12. All right, so there is nothing in the intersection here. There are no elements that are in both sets. So we have the empty set. The intersection of A and A complement is the empty set. Now remember, this means that they are disjoint. When two sets don't have any common elements, the term we have for that is they are disjoint sets. Right, if we have A union A complement, we're looking for any elements that are in either set. So if you have sets given in roster notation, one of the easy ways to deal with the union is just write down the first set. 1, 2, 4, 5, 7, 8, 10, 11, 13. So I just copied down my set A, and then go look at A complement and write down anything that hasn't been written down yet. Let's see, 3 hasn't been written down yet. 6 hasn't been written down yet. 9 hasn't been written down yet. 12 hasn't been written down yet. Okay. Now, it's also the case, we saw in this example that the intersection of a set with its complement is always empty. Here, the union of a set with its complement is always the universal set. All right, moving on to the next example, we have a more interesting intersection. So we have a couple things going on here. We have the intersection of A with C, and then the complement of that. All right, so we have these nice grouping parentheses that tell us that we should do this intersection first. So that is what I will do. So The intersection, remember this is the intersection of two sets. We want all of the elements that are in both, or a lot of times this is taught using the keyword and. We want the elements that are in A and in C. We want the element to be in A and we want the element to be in C. Okay, so let's see. We have, I guess A and C are both approximately the same size. So when we're looking at intersections, the way that I think about intersections is I just focus on one set. So I will focus on the set A and go item by item and see if the element of A is also an element of C. So the element 1 is an element of A, but it's not in C. So it's not in the intersection. The element 2 is in A, but it's not in C. So it's not going to be in the intersection. The element 4 is in A. It is also in C. So the element 4 is in both of those sets, so it's going to be in the intersection. Let's see, 5 is only in A. 7 is in A and C, so it will be in the intersection. 8 is only in A. 10 is in both, so it will be in the intersection. 11 is also in both, and then 13 is only in A. Now, the nice thing about that strategy is once you've done that with the one set, like I said, we focused on the elements of A to determine if they were in both. Once you've done that with one set, you don't really have to do that again with a second set. We've already identified all of the elements of C that are also in A. Okay, so this set that consists of the elements 4, 7, 10, and 11, that is A intersect C, or the intersection of set A with set C. And now we want to find the complement of that set, which means we have to refer back to our universal set to find all of the things that are not. Remember, the complement is all the things that are not in this set. Okay, so it looks like the elements that are not in that set, 1 is not in that set, 2 is not in that set, 3, 5, 6 is not in this set here, 8 and 9, and 12 and 13. All right. So we followed the order of operations here, found this intersection first, and then took its complement. All right, the next example, we're getting really beefy here. We got a lot of things going on. Actually, I think this is supposed to be 2 examples. This is supposed to be 2 examples. Yeah. So it's not quite as beefy. All right, we fixed it. It was an emergency, but then we fixed it. We want the union of A complement, there's the union right there, A complement with C complement. Now, just like with algebra, where you learned the PEMDAS, that said like exponents, aside from parentheses, exponents are the first thing that you look at. We can think about that the same way with these complements. We want to do the complements first and then find their union. All right, so I think we already found A complement somewhere. Yeah, we did it up here. A complement was 3, 6, 9, 12. C complement, oops, I don't want equals, I want the union. C complement is going to be all of the things that are not in C. So we got to look at C and figure out all the things that are not in C. All right, so let's see. 1 is not in C, neither is 2. 5 is missing from C. 8 and 9 are missing from C, and 13 is missing. All right, so those are all the elements that are not in C. That would be C complement. And now we're doing the union. We want all of the elements that are in either of those sets, or perhaps both. Remember, with the union is or, we want all the things that are in A complement or in C complement. So if we just march down A complement first, we can just copy down that set, 3, 6, 9, 12. And then when we go down to C complement, we're just going to write down all the elements that haven't shown up yet. 1, 2, 5 hasn't shown up yet. 8 hasn't shown up yet. 9 was already there, so we don't need to write it down twice. 13 is in C complement and hasn't shown up yet. All right, so there is our A complement union C complement. And it's okay. I think I left a set unordered up here. It's okay to... The order doesn't matter. When we're talking about sets, the order in which we list the elements doesn't matter. But if it makes you more comfortable to write down the elements in order, it's not wrong to do that either. Okay, on to the next example. We want to do A intersect B union C, and they gave us these parentheses here that says, find the intersection of A and B first. So we want to find all of the elements that are in both of those sets. All right, so I'm going to maybe do that off on the side here. A intersect B. Again, we're looking for all the elements that are in both sets. I have my roster notation for A written here, and my roster notation for B written here. B is a smaller set, so maybe I'll march down B. Let's see, 4 is in B. It's also in A. So 4 is in the intersection. The next element in B, 6 is in B, but it's not in A. So 6 is not in both. 8 is in B, and it's in A, so it's in both. 8 is in both sets, so it will be in the intersection. 10 and 12 are also in both sets. So there is A intersect B. All right, so we've done that work. Let's go ahead and write down the work that we've done so far. 4, 8, 10, 12. We're taking the union of that set with set C. So we wrote down C complement here, so let's just write down, we can reverse engineer C, 3, 4, 6, 7, 10, 12. Sorry, 10, 11, 12. All right, so there's our set C. And then if we want the union, we're taking the union of these two sets. We want any element that's in either one of those sets. Again, the key word is either, or you can say or. Now, I guess it makes, here's another, I mean, you don't have to do it the way that I did it up here, where you just copy down one set and then write down the other. Like write all the things down from the other set that you haven't written down yet. That's the easiest way. But you can just kind of look and say, let's see, 1 and 2, we know which things we're supposed to be looking for. 1 and 2 aren't in either of those sets, but 3 is in C. 4 is in actually both of them. We only really need it to be in one. 5 isn't in either of those sets. 6 is in the second one. 7 is in the second one. 8 is in the first one. 9 isn't in either of those sets. 10 is in both of them. For the union, we only need it to be in one or the other. If it happens to be in both, I guess you can think of that as being a bonus. 11 is in the second set. 12 is in both sets. 13 isn't in either set, so it's not going to be in the union. One way to think about the union is, a lot of times in the real world, when we hear this word union, it's used in the context of marriage, and when two people get married, you take their possessions and they combine their possessions. All right? And so the combined possessions of the pairing, you wouldn't necessarily need, 2 toaster ovens. All right? So when you're thinking about all the different things that 2 married people are going to have, you don't necessarily want to consider the doubles. Okay? All right, this last one, we've got a few things to do. We have A intersect B complement. A intersect B complement. So everything that's in both A and not in B. All right, or you can think of A but not B. A and not B, the not comes from this complement, or A but not B is another way of saying that. All right, so one way to think about this particular, we can kind of do a shortcut here. I could write down B complement, and then find all the elements that maybe I'll do that with the second one. All right. The shortcut here is if you think about A but not B. It's like, I like A, but I don't want any of the stuff that's in B. You look at A and throw away all the stuff that happens to be in B. All right, so that's a shortcut here. All right, so let's look at A. Let's look at A and throw away all the things. So A but not B. Look at A and throw away the things that are in B. We have 1 is in A, but it's not in B, so we want to keep it. 2 is in A, and it's also not in B. We're looking at B up here. 4 is in A. It's also in B, though, so we got to throw it away. We don't want things that are also in B. Okay? A and not B. 5 is in A. 5 is also not in B, so it's going to be in A but not B. 7 is in A. It's also not in B. 8 is in A. It's in B, so we got to throw it away. 10 is in A. It's also in B, so we got to throw it away. 11 is in A. It's not in B, so we get to keep it. Same for 13. So there is our A but not B, or the intersection of A with B complement. 1, 2, 5, 7, 11, 13. And then we want the union with A complement intersect B. They're the intersection of A complement and B. So we want the things that are not in A and in B. All right, so we'll do that one. We'll do that one more explicitly. Let's see. We have A complement. So we want A complement and B. We have A complement here. And so we can look at the things that are in both A complement and in B up here. 3 is in A. It's not in B, though, so we don't want it to... Sorry, 3 is in A complement. It's not in B. 6 is in A complement, and it's in B. We want the things that are in A complement and B. So 6 is in both of those things. 9 is only in A complement. 12 is in A complement, and there it is in B. So 12 is in both. All right, so the only things that are in A complement and B are 6 and 12. So I just want to point out that we used a little bit of different thinking to do this one compared to that one. And it's reasonable if you were kind of confused as we jump from one way of thinking about the problem to a different way of thinking about the problem. All right? If you were confused, I would encourage you to go back and maybe slow it down a little bit and listen carefully to the descriptions that we were doing. Okay? Again, the way of thinking here is A but not B is all the things in A, and then we take all the stuff in A and then throw away the stuff from B. All right. I know it says B complement here, but we were more focused on B in that case. A, throw away B. And if you were to take this class at IUPUI, they have a special notation for this. A, throw away B. All right, or another alternative notation, A throw away B. All right, but that's not part of our class. It's just an illustration that we can maybe codify this idea with notation and focus on that notation. All right, so if you didn't like the thought process that we were doing for this first set, if you prefer the thought process that we were doing with the second set, that was more focused on the individual operations, the complement and the intersection, go with that second thought process. The second thought process is the one that's more universally applicable. Okay, moving on to the next question. Given two sets A and B, draw Venn diagrams representing the following sets. So we were just dealing with A complement intersect B with some explicit sets here. Let's see if we can get a visual representation of what that set might look like. So we have a Venn diagram involving two sets A and B. So the entire rectangle is our universal set. And then we've got two circles, one representing A and one representing B. Okay? So the A complement, we're looking for the visual depiction of the things that are in A complement and B. All right? Now I think it's easier to look at B first. If we know that our element is in both sets, we know that we're restricting ourselves to being in the B circle. We're inside the B circle. Again, this intersection means we're focusing on only the things that are in both sets. Okay? So already the intersection you can think of as kind of being a restriction. It's more restrictive. Okay? We have the restriction of, we need to be in the B circle, but we also need to be outside of the A circle. That's what A complement is. A complement would be the stuff outside of the A circle. So if we look at the B circle and then shade everything in the B circle that's outside of the A circle, we're looking at the crescent part of B. That's the visual or Venn diagram depiction of that set. So you can kind of see where I was getting at when I was thinking about, like, if we write it as B but not A, right? The A complement is not A. These union and intersection are commutative. If you remember commutivity in algebra, x plus y is the same as y plus x. You can switch the order of the operation. Unions and intersections are commutative, so you can flip them. All right. It's one of the fun things about some of this material. You can think about it in terms of algebra. It actually is algebra, just algebra for sets instead of numbers. Anyways, we're going to get off topic here. I was thinking about, in my first way of thinking in the previous problem, B but not A. Is how I was thinking about B intersect A complement. I was thinking, okay, take all the stuff that's in B and then throw away this football-shaped piece that also happens to be in A. Throw away all the A stuff and just keep the stuff that's only B. That's another way of expressing that idea using English language. Okay? Another way of approaching these Venn diagram problems is to shade the sets individually. So A complement would have been everything outside of A. And then if I use a different color, it's really helpful to have different colors. Just switch colors to blue. B would be that circle right there. And then the intersection is the overlap. Okay? The part of that gets shaded both red and blue. And that's not hard to see. Okay, the part that's shaded both, I guess that would be purple, right? Red and blue make purple. There we go. There's purple. All right, so the purple stuff, there's our purple right there. All right, so there's where we get our A complement intersect B. We can use, it's even easier with the union in example B. I'm going to go back to my red. In example B, when you're doing the union, it's even easier. Unions are a lot easier than intersections. Unions, you just get to write down stuff. You take all the stuff from A, and then you add it to the stuff that's in B. Union, we just talked about. There's kind of a correspondence between these set operations and for the set operations and operations for numbers, and union acts a lot like addition. There's a lot of it's not an exact analogy, but union for sets acts a lot like addition for numbers. But anyways, when we're doing A union B complement, we just, all right, shade in the A part. With this union, we want all the elements that are in either of those sets. Okay? And so once we've shaded something, we know we get to keep it. It's kind of like when we write down the sets in roster notation, just write down everything that's in A and then write down everything in B complement that you haven't already written down yet. Here we shade in A and then we shade all the parts of B complement that we haven't already shaded. Well, B complement itself, it doesn't matter if we shade things twice, that's okay. B complement is everything outside the B circle. Okay? So, everything that's shaded now, I guess if we were going to, I maybe should have done that using my colors again. I like that purple better than that other purple. The stuff that's shaded, period, would be everything except for, actually that's kind of like the opposite, right? This is kind of the opposite of what we shaded up here. And so seeing, all right, that's interesting. We talked about De Morgan's laws. Here's another little bit of this is algebra for sets. All right, the set that we shaded in part B, A union B complement, is the opposite of the thing that we shaded in part A. Right? And so that's interesting. If you think about like doing some algebra and treating these things like exponents, it looks like, in general, I'm going to use different letters here. If I have sets E and F, if I do E union F complement, that's the same as E complement intersect F complement. So both of the sets get complemented, and the union turns into an intersection. And that's algebra. That's kind of like a distributive property or something. Some kind of exponent law. Some kind of exponent law for set operations. Now, that's not something that you have to have memorized. It's just a nice fun fact. But I guess the point here is we were able to illustrate that fact using Venn diagrams. Okay? So that was fun. Moving on to C. Hey, we just kind of did this, right? We just kind of did that, right? We think we just developed this new algebra. This was unintended, by the way. Or maybe not. I wrote these notes a long time ago, so maybe at the time I wrote them, it was intended. According to the algebra for sets that we just determined, A union B complement should be the same as A complement intersect B complement. But let's just go ahead and look at that. So when we're doing complements with Venn diagrams, we have our sets A and B and our universal set. We could think about, okay, what does A union B look like? Well, that is all the stuff that's inside either of the bubbles. So the red shading there would be A union B. If we want A union B complement, we need to shade the unshaded portion of that. Everything outside the bubbles. All right, so the purple would be A union B complement. If we focus on this side of the equation, we want everything that's not A and not in B. Or you can think about that as neither. So not A and not B it means when we dissect the English language, that means neither A nor B. All right, so the purple here is definitely neither A nor B. Okay, so there's some Venn diagrams. We also got to, focusing on the language here is also good too. Later on, when we do more interesting counting problems and probability and statistics problems, we're gonna have to work with the language and actually go from the English language back to some kind of set theory idea a lot more often. And so getting comfortable with the language, understanding how to use set theory to describe the language is important. So let's look at our next example. Given 3 sets, A, B, and C, draw Venn diagrams representing the following sets. So we need a 3-set Venn diagram here. We have a universal set. For our 3-set Venn diagrams, we end up with kind of a Mickey Mouse looking thing-ish. We have set A and B. That part of it looks like the normal 2-set Venn diagram. And then we throw on another C circle down here. Okay? So, this complement here, the C complement, we want to consider that kind of first. So not C, we want A and B, but not C. All right, now the A and B part, blue, the A and B part is this football shape. All right, so we got our A and B part, and then the but not C. We want to throw away the part of this football that overlaps with C. Right? This is the part that overlaps with C. We want to get rid of that. And so the part of A and B that we want to keep is the top half of that football shape. All right, so there's our A and B, but not C. Another approach here is to do what's called coloring by numbers. If you were like me, did some paint by numbers when you were a kid. Here we can color by numbers. Actually, it's going to be coloring by letters. There's a bunch of regions here, and we're just going to label each individual region of this with a letter. And start with X. X, Y, Z, U, V, W, S, and then T. So there were eight regions here in our 2-set diagrams. If we go back, because this will also work for 2 sets, you can see that there's 1, 2, 3, 4 regions. So there's a nice fun pattern that we're going to be able to explore when we do some counting stuff. All right, so there are 8 regions here. Now we're going to pretend this isn't technically true. We don't know really anything about A. X is not an element of A, but we're going to treat it like it is. Okay? So I'm going to put these in quotation marks. A is, we're going to say that it is the set consisting of X, Y, U, and V. It's not really, though. It's not really, though. We're going to treat it like it is. B has the pieces Y, Z, V, and W. And C has the pieces U, V, W, and S. All right, so we had to do C complement first. If I write down C complement, that's going to be all the things that are not in C. So we have X, Y, Z, and T. Then if I do A intersect B, once we get that C complement, we move from left to right. So A intersect B, all of the things that are in both. Looks like the overlap here is Y and V. Those are the only elements that are in both of those sets. And then if I do A intersect B, there's some kind of hidden parentheses up there. That would be YV intersect C complement, we determined was X, Y, Z, and T. Again, all of the elements that are in both, because of the intersection here, the only element that's in both is Y. And that's why we shade that region up there. So this coloring by letters, which compares to paint by numbers, is you can kind of write down these fake sets. They're not. That's not really the elements of A, but for the exercise, we're able to pretend like those are the elements of A, and just do basic set operations like we did back at the beginning. So if you prefer these kinds of set operations, that can be helpful for shading in some Venn diagrams. In my opinion, the easiest way to get the Venn diagram shaded in is to understand how to translate back and forth between English and set notation, and also understand how to interpret the English. Like I think one of the things that the Math 135 teachers underappreciate is we take this understand the English language business a little bit for granted too much. Like we understand it because we've been doing it. We understand how to interpret these words in the context of Math 135 because we've been doing it for a lot longer. Okay, looking at part B, A or B intersect C complement. A or actually I would say, how would I translate that? I just bragged about my ability to do the translations. Since we got a complement there, I would be inclined to think about this A but not B and C. Okay? So that's what I'm thinking about. In terms of just kind of English language thinking. Oops, that's a union. That's a union. It's not but not, it's or. A or. Yikes. Sorry about that. The union makes everything easier. A or. Because we just have this A or, I can right off the bat, let's shade that in with the blue. I can go ahead and shade in A because we have that union. I know I'm going to get to keep everything that's in A. Now, to deal with the second part, I want not B and C. B and C itself getting all kinds of crazy with the colors. B and C would be inside the green football, right? B and C, all the elements that are in both would be inside the green football. So not B and C would be outside the green football. Okay? So basically, if we were to shade in everything but that kind of lower right-hand part of that green football, that would be this set. All right, let's start over. I thought that was going to pick a bigger eraser. Medium eraser. Come on now. Let's just go back to what we know how to do. Okay. So let's go back and do this one using the paint by, or the color by letters method. Universal set with 3 subsets, A, B, and C. And we'll just go ahead and label these regions the same as we did in the previous problem: X, Y, Z, U, V, W, S, T. And then let's see, A would be X, Y, U, and V. Union. B intersect C is V and W. Want that to be the complement. X, Y, U, V. The complement of V and W would be everything on the outside: X, Y, Z, U, S, and T. I guess here our universal set is just X, Y, Z, U, V, W, S, T. So everything that's not V and W. And then for the union, we start by writing down the first set: X, Y, U, V, and then everything from the second set that we haven't already written down. We already written down X, we've already written down Y, Z, we've already written down U, S, and T. And then we can go back up here and say, all right, shade in the X part, the Y part, the U part, the V part, the Z part, the S part, and the T part. So everything except for W. All right, so obviously the color by letters takes a lot longer, but I think it's a little bit more of an established process. You know, if you struggle with the translation, it's a method for getting the job done. Translating's hard. I mean, you just saw me kind of mess up a couple times in the translation. So translating, it requires some work. This color by numbers is kind of a shortcut. It's kind of one of these bad shortcuts. It's a good way to get like a problem done on a test, but it's a really bad way to start to understand the important stuff, like working with the language. All right, and there's one more example. This is kind of a big one. Yep. We want let U denote the set of all Ivy Tech students taking classes this semester. Use set operation and notation with the following sets to describe the given set. So this is where we're going to get to practice understanding the language. All right, so we have 4 sets. Sorry, we got the universal set of all Ivy Tech students taking classes. We have the set F, which is the set of all female Ivy Tech students taking classes. Again, there's this underlying assumption that all of these sets are subsets of our universal set of students taking classes. M is the set of students who are taking finite math. E is a set of students who are employed. And G is the set of students who play games. We want to use set notation to describe the set of students who are female gamers. All right, so we have two ways to describe students, females and gamers, and we want the set of students who satisfy both of those descriptions. We want them to be both females and gamers. And so that would be the intersection. The intersection of females and gamers. Part B, the set of students who are male or not taking finite math. There's two keywords here. Or and not. Okay, so the first, we want any student who satisfies either of those two descriptions, or possibly both. There's probably lots of males who are also not taking finite math. They satisfy both of those. We only need them to satisfy one or the other, or perhaps both. This or is the union, and the not is the complement. Not taking finite math. So male would be M. Or not taking male is, sorry, we don't have male. M stands for taking finite math. Oops. Actually, in this context, I guess we have to assume that male means not female, which is maybe not quite as woke as we want to be in Math 135 in 2019. Well, let's just go ahead and go with it. So we want not female or not taking finite math. So not female would be female complement, or not taking finite math would be M complement. The students who are not taking finite math would be M complement. All right, so yeah, I guess this is a not very progressive example, but let's try not to get too upset about it. In C, we want the set of students who are employed but are not taking finite math this semester. So the employed students would be E, but not is the same as and not. So the and not taking finite math would be M complement, the complement of the people who are taking finite math. That would be a weird way to describe that set, right, though? Employed but, I mean, I guess, that'd be a weird way to describe that set in the real world. All right, and then the last one here, the set of all students taking finite math who are neither female nor employed, okay? So we want them taking finite math. That would be the M set. We also want them, okay, we want them also to be not female nor employed. They're not female and they're not employed. And not employed. So I think one way, we have our complements there, we just need to get our intersections. Remember, and corresponds with intersection. We want them also to be not female and not employed. Remembering some De Morgan's laws, we could also describe this as M intersect F union E complement. That's De Morgan's law, or one of De Morgan's laws says F complement union E complement, intersect. F complement intersect E complement is the same set as F union E complement. All right, so I think this is kind of what they were going for with this second, who are neither female nor employed. Not female or employed. I think that's what they were going for. But we have a couple different descriptions, and both of them are fine. The only thing is in the context of maybe a multiple choice question, you might need to be able to realize which of these two, like they're not going to present both of them, they're going to present one or the other, and so you might need to be able to work with both interpretations. Okay, so I think that gets us to the end of this set of examples. If you have any questions about any of these examples, please don't hesitate to contact me. If you have questions about any other problems on the 6.1 homework, don't hesitate to ask. If enough people ask about the same problem, I'll make another video about that specific problem.